Section 2-3, the limit theorems. The objective for this second half here is use algebraic techniques to evaluate limits. Now the topics we're going to cover here in this second half are not actually in the book. They're not in Section 3, they're not in Chapter 2, but I think this is the place where they best fit. So that's why we're going to cover them here. But definitely if you're looking in the book for these topics, you're not going to see them in Section 3 of Chapter 2. All right, so let's take a look at some algebraic techniques that we can use to evaluate limits. And the first technique that we're going to use is what we call the substitution method. And we're going to start with this method because actually every single limit problem that we'll encounter will start out with this same method. You always try substitution first, see that where it leads you, and then take the appropriate path to get the correct answer, of course. So the substitution method, as its name indicates here, you find the limit by substituting the given x value into the function. Again, if you go back and recall what the definition of a limit is, it's the y value that your function is approaching as you approach a given x value. So this technique is just saying, well, plug in the x value, see what you get for the y value, and that would be your limit. So let's take a look at an example of that. Here we have the limit as x goes to 2 of x squared plus 4x minus 1. Now again, the technique, substitution, just simply says take each of the x's there and substitute in the value of 2 in this case that we're letting x approach and see what you end up with. So let's try that out. This would be equal to, I'm going to go ahead and write this out in this form here. Normally you probably wouldn't write this all out, but just so you see the substitution showing up here, I'm replacing the x with 2, so it's 2 squared plus 4 times 2, and then minus the 1. So you end up with 2 squared is 4, plus 4 times 2, that's 8, so 4 plus 8 is 12, minus 1 would end up giving us 11. And that, in fact, right there is the limit of this function as x approaches 2. Okay, and many functions that we'll look at many of the points in those functions, we can do this exact same thing. However, there are some problems where this won't work. All right, and so we need to have some other techniques that we're going to use. So let's take a look at some other techniques here that we use to solve these algebraically. And before we look at the next technique, actually, we need to talk about this indeterminate form. The indeterminate form here is 0 divided by 0. Now, there are actually several indeterminate forms that we'll talk about later on in the book. We'll cover all of them, but for right now, we're just going to focus on this one. And we're not changing any of the rules that you know about division by 0 here. Again, we're talking about a limit. So when we say that it's 0 divided by 0, we're not really saying that you're actually getting to 0, but rather we're getting closer and closer and closer to 0. It's some fraction that has a numerator that's approaching 0 and a denominator that's also approaching 0. And thus the limit is approaching this form of 0 over 0 is what it looks like. So it's a really, really small number divided by another really, really small number, and it has an unknown value. That's what the indeterminate form. We can't determine its value from the form it's in. And so if that happens, we need to have some additional techniques that we can use to evaluate those. So the first technique is known as the factoring method. And I guess as its name would indicate for you here, it's going to involve some factoring. You're going to factor the function to cancel common factors. That's the key. Common factors can be canceled. We're talking about canceling common factors in the numerator and denominator here. And then once you're able to do that, you can then go back to that substitution method and substitute in the value of x. And you should be able to evaluate that. Okay, so let's see if we can try that out here with an example. Let's say that we have this function here, the limit as x approaches 1 of x squared minus 6x plus 5 divided by x minus 1. Now, the first thing that you do with every single one of these problems is you start out with that substitution method that we just talked about to determine what value this function is approaching. So I'm going to let x go to 1. In the numerator, I will have 1 squared, which is 1, minus 6 times 1, that's a minus 6. So 1 minus 6 is a negative 5, plus 5 gives me 0. So the numerator of this thing is heading towards 0. Do the same thing for the denominator. Of course, just 1 minus 1, that gives me 0. There's that indeterminate form we just mentioned. So when this happens, we've got to do a few more things in order for us to be able to find out what the value of that limit is. Again, what we're saying here is if we end up with this form, we can't determine its value, thus the name indeterminate form. All right, so let's try this factoring method. So we're going to take the limit as x approaches 1. And in the numerator there, because I actually plugged in 1 in the numerator and got 0 out, I actually found out some information about this polynomial that's in the numerator. I found out, first of all, that it has a 0 at x equals 1, but at the same time, if it has a 0 there, I also found one of its factors. That is, I know that x minus 1 must be a factor of that numerator. And the question is, what's the other factor? Now, for some functions like this one here, it's probably not too difficult to just factor that. However, you can use synthetic division. We talked about that at the beginning of this section, so you can certainly go back and use that technique to help you factor it. Whatever you need to do to get the other factor, but we should be able to find that the other factor is going to be x minus 5. Double check to make sure that, in fact, that product gives you what you started with there, but in fact, that's what we'll end up with. And that's all over x minus 1. And now you can see that in both the numerator and denominator here, I have a common factor of x minus 1. And we're going to cancel those two guys out. And once we cancel those two out, we in essence eliminate that 0 over 0. The 0 over 0 that we are getting was because of the fact that I had a factor of x minus 1 over x minus 1. That's the whole reason for that 0 over 0. Once I cancel those two factors out, I eliminate the indeterminate form, and now I should be able to evaluate this limit. In fact, let's see what we end up with here. Once we cancel those out, I'm going to go ahead and rewrite this one more time here. You don't necessarily have to rewrite it, but all we'd be left with is just the function x minus 5 that we're finding the limit of as x goes to 1. And so now, going back to substitution, substituting in 1 for x, I end up with 1 minus 5. That turns out to be a negative 4. Notice, by the way, that once I actually do the substitution there at the end, I don't write down the limit notation. So that's where I actually get rid of the limit notation when I actually go through and substitute in that value of 1. And that, in fact, is our limit as x goes to 1. The function's not defined at x equals 1. It actually has a hole in the graph there, a removable discontinuity. But the function is approaching a value, and that value is negative 4. All right, let's take a look at the next technique here that we'll use. And the next technique requires that we understand one thing about binomials, and that is the conjugate. And you may recall that the conjugate of a plus b is just a minus b. So what that means is, if I have a binomial that's in the form of a plus b, I can rewrite that, or not rewrite it, but I can write the conjugate as a minus b. And the nice thing about conjugates, and in particular we're going to multiply conjugates, when I multiply, I'll go ahead and write this over to the side here. When I multiply a plus b times a minus b, you may recall that ends up with the middle two terms canceling out. So this ends up giving us a squared minus b squared. There is no middle term. Normally when you multiply binomials, you end up with a middle term there. There's 3 terms you end up with. Here we don't, because of the fact that they'll cancel out. That's going to be the important part for us, or the reason why we want to multiply by a conjugate. All right, so this next method is known as the rationalization method. And the rationalization method means that we're going to multiply the numerator and denominator. Of course, you got to multiply both of those by the same thing in order for us to not change the problem. But multiply the numerator and denominator by the conjugate. Sometimes this is called multiplying by the clever form of 1. Remember, you can multiply by 1 and it won't change the problem. So as long as I multiply by a quotient or a fraction where that's equal to 1, then I don't change the problem. So as long as the numerator and denominator are the same, I'm multiplying by 1. So that's what we're going to do here for these problems. Rationalize this function here. All right, so let's take a look at an example here. We call this rationalizing because of the fact that you've got a radical in there, that square root. But if we want to find the limit as x goes to 1 of the square root of x plus 3 minus 2 all over x minus 1. And again, the place to start with this every single time is to consider what happens if I substitute in this value of 1. If I get a number out, I'm done. If I get that indeterminate form, I know I've got some extra work to do here in order to answer this one. So let's plug in 1. I'll have the square root of 1 plus 3. That's the square root of 4 is 2. Minus 2, the numerator is heading towards 0. And the denominator, 1 minus 1, that's also heading towards 0. So there's that indeterminate form. As you probably would have guessed, that we're probably going to end up with an indeterminate form on this one as well. And that's what we have there. So let's take the limit as x goes to 1 of the square root of x plus 3 minus the 2 over x minus 1. Now the part with the radical, this is why we call it the rationalization method, the part with the radical, in this case the numerator, that's the part I want to focus on, and I want to multiply by the conjugate of that part. So the denominator, of course, I could multiply by the conjugate of x minus 1, that is multiply by x plus 1, but that's not what I want to do. I want to focus on the part with the radical. Okay, so the numerator is what I'm looking at. I'm going to multiply then by, think of the square root of x plus 3 as the a part, and then you're subtracting, and then the 2 is the b part. So in other words, the conjugate of this is the square root of x plus 3 plus 2 all over the square root of x plus 3 plus 2. Again, I'm multiplying by a clever form of 1 there. Numerator and denominator are the same, thus it's equal to 1. Thus I will not change the problem when I multiply this. All right, now in the numerator I'm going to actually multiply this out. And the reason I'm going to do that in the numerator is because that's where the conjugates are. So I always want to multiply the two conjugates together here. So square root of x plus 3 times the square root of x plus 3, that just gives you x plus 3. Again, you can multiply this whole thing out and get the middle terms, and you'll see they'll cancel out. I'm just going to skip right past that and just multiply the negative 2 times 2 gives me a minus 4. That's my a squared minus b squared. And for the denominator, I'm going to leave him in this factored form here as x minus 1 times the square root of x plus 3 plus 2. Leave him just like that. Now in the numerator, I can see I can simplify this a little bit. That is, I have a plus 3 and a minus 4, so I'm going to combine those two. You could certainly do that in that same step there, but I'm going to write it separately so you can see what's happening. 3 minus 4, of course, is a negative 1, so I end up with x minus 1 in the numerator over the x minus 1 times the square root of x plus 3 plus 2 in the denominator. And generally, this is what we're looking to have happen here, that in the numerator, I now see I have a factor of x minus 1, and the denominator also has that same factor. And so those guys are going to cancel out. It's going to go back to that factoring method that we just talked about. You'll notice that as we go through here, we're going to use these previous steps or previous methods in order to solve these new types of problems. So cancel out the common factor. And again, once you cancel that out, that right there was the whole reason, if I go back up to the original, it's the whole reason that I had this form of 0 over 0. Once I cancel those common factors out, I end up with, I end up getting rid of that indeterminate form, and thus I can determine its value. Okay? The fact that I'm letting x go to 1 tells me that I know I'm looking for common factors of x minus 1 to show up. In other words, whatever you're letting x approach here, I know that I need to get factors of x minus that value to cancel out. So that's what we have here. I'm going to rewrite this again. You don't necessarily have to rewrite it, but just so we can see what we end up with. Realize this is 1 over the square root of x plus 3 plus 2. And now, because I've gotten rid of that indeterminate form, or I've canceled out the common factors and thus gotten rid of the indeterminate form, I can just use my substitution method. This always ends with that substitution, which again, once I go and substitute in, I don't write down the limit notation anymore. And I have 1 over the square root of 1 plus 3, that's the square root of 4, which is 2, plus another 2, gives me 1/4. So the limit of this thing is approaching a value of 1/4, 0.25. All right, let's take a look at one last method here. And the last method is dealing with complex fractions, the complex fraction simplification method. And a complex fraction, remember, is a fraction that has a fraction in either the numerator or the denominator, or both. So it's a fraction of fractions, in other words. Complex fraction. So the technique here is use factoring, common denominators, or clever forms of one, whatever it's going to require in that problem. Just depends on the problem as to how you do it. Most of these we're going to see that they involve finding common denominators to simplify the fraction. And then once you simplify that fraction, you can then usually find a common factor to cancel out. And once you do that, you can evaluate this thing. Now again, if you plug in values right from the beginning and you get some number, you're done. But if you get that indeterminate form, I know I've got some extra work to do here in order to solve this. So let's take a look at an example here. Let's say that they ask us to find the limit as x goes to 3 of x minus 3 divided by 1 over x minus 1 over 3. So if we check to see what value this is approaching, as x goes to 3, the numerator, 3 minus 3, that's heading towards 0. And the denominator, 1/3 minus 1/3, that's also heading to 0. There's that indeterminate form. So if that's the case, that means we got a little bit more work to do. Let me just rewrite this problem, and we're gonna do a little bit of work with the denominator. Again, if it's a complex fraction, usually it's going to involve finding common denominators either where in the numerator or denominator, wherever that extra fraction shows up. So in this case, it's in the denominator. So I'm going to multiply this first term in the denominator by 3 over 3. This is an easy way to, 3 over 3 is what I want to multiply by. This is an easy way to get a common denominator. Take the other fraction's denominator, which is 3 in this case, and multiply it by the first fraction. And then the second fraction, I'm going to do the same thing. Take the denominator from here, which is x for the first fraction, and multiply by x over x. Again, those are clever forms of 1. They won't change the problem when I multiply by 1, but they will get me a common denominator. So I have the limit as x goes to 3 of x minus 3 divided by, I end up with 3 over 3x minus x over 3x. Again, you can see that we have our common denominator now in the denominator part of this complex fraction, which was the whole point there that we just went through to get a common denominator. So let's combine those, and you could have done this obviously in one step. I'm just breaking it up so you can see the steps here involved. So we have x minus 3 in the numerator, and now I can write the denominator as 3 minus x over 3x. And I can see that I have an x minus 3 in the numerator part of this. I also have an x minus, or 3 minus x really, in the denominator. Those are close to the same factor that I want to cancel out. I got a little bit of work to do with it. So I'm going to take the limit as x goes to 3. And if it helps you, you can rewrite a quotient like this as a product, remember. The x minus 3, think of that as being x minus 3 divided by 1. I'm going to put a divided by 1 here. I'll put that in parentheses so you can see that. That's the same thing. Actually, I should do that in a different color here. Let me just go back and put that in a different color there so you can see that it's the same thing as dividing it by 1, of course. And so I can rewrite this as a product. I just take the numerator and leave it alone. So I'm going to write it as x minus 3 over 1. You don't necessarily have to write it over 1, but sometimes it's helpful if you write it as a fraction. And then you reciprocate the denominator and multiply. So I'm going to take the reciprocal. Just flip that fraction over, 3x over 3 minus x. All right, if you need to do this in order to get rid of the x minus 3's, do so. If you're okay with working with a complex fraction and doing it correctly, that's fine too, whatever works for you. The one last thing I want to do here before I start canceling stuff out is I want to rewrite one of these two factors. I have an x minus 3 and a 3 minus x. I need those to be the same. So I'm going to take care of the 3 minus x and rewrite it here slightly. It wouldn't really matter which one of the two you picked to do this with. But in the denominator there, the 3 minus x, I'm going to factor out a negative 1. If I factor out a negative 1, or just a negative there, the 3, of course, becomes negative, so it'd be a negative 3. And if I factor out the negative in front of the x, it, of course, becomes positive. So you end up with a negative 1 times negative 3 plus x. Of course, I can rewrite that. Again, I'm taking several steps so you see what the process is here. You don't necessarily have to write down all these steps every time. But I can rewrite that then in the following way. I'll just put a negative sign out front there instead of negative 1. And then instead of negative 3 plus x, that would be the same as x minus 3, just changing the order of those two. And we get x minus 3 there. And now I can see that I've got a common factor. This is the key, though, that you realize that there's a negative that shows up there, that when you've got a x minus 3 and a 3 minus x, there's somehow a negative that's got to show up there when you go to cancel those out, okay, or that stays in the problem. And once I do that, I can now evaluate that limit. Again, once I get rid of the x minus 3's, I've gotten rid of my 0 over 0, that indeterminate form. So now I'll go back to substitution here. I'm just going to rewrite this as 3x divided by, really I've got a negative 1 in the denominator. And now if you let x go to 3, I'll end up with 3 times 3 is 9 divided by a negative 1. Again, notice I don't write down the limit notation because I've actually evaluated the limit right there. And then this turns out to be, of course, equal to negative 9. That's our limit. Okay. Those are 4 techniques that we use to algebraically evaluate limits. And that is the end of this section for us.